Okay, it actually gives me immense pleasure to be talking about cosmology with gravitational waves at this meeting in ICTS, because when I first started working on gravitational waves about 4 years back, I started working on some aspects of doing cosmology with gravitational wave observations. We already heard from the speakers this morning about GW17, 0817, a BNS merger that came with an associated GRB and an optical counterpart that got promptly localized to NGC 4993 in the constellation of Hydra. And if you can see the background of my slide, it shows the constellation of Hydra, the water snake, with the location of NGC 4993 around where I have fireworks written on my slide. This galaxy itself is too low to be observed from here in Amsterdam, but with a small telescope, with a small amateur telescope from India, you can easily see the host galaxy itself. I'm not talking about the optical counterpart, but the host galaxy itself. Hubble's law is actually a very simple relationship between the recession velocity of galaxies in our local universe with the distances to the galaxy. And the constant of proportionality is the Hubble parameter. It's given by this simple expression that I have on the slide. This recession of the galaxies away from each other, away from us, would imply recession of galaxies away from each other, and this can be connected to the stretching of space-time itself, and hence the expansion of the universe. So the Hubble parameter is the parameter that characterizes the rate of expansion of the local universe. What is usually measured in terms of the recession velocity is the redshift of the galaxies receding, and the cosmology and this Hubble velocity is related to the cosmological redshift by this expression. To the bottom right of the screen, I have the original plot from Hubble from 1929, where he has the distance on the x-axis and velocity on the other axis. Unfortunately, he has wrong units on the y-axis. He labels it as kilometers instead of kilometers per second, and he tries to fit a straight line through these points in recession velocity and distance to get the Hubble parameter. Note that he also has a significant overestimate. If you would just follow the slope on his line, then you would get a Hubble parameter of about 500 kilometers per second per megaparsec, while the value now is closer to 70, which is 7 times smaller. So this itself sort of hints that this is a rather difficult parameter to measure. I move over to my next slide, slide 3. And here I talk about the current measurements, the state-of-the-art measurements of this Hubble parameter. Now, there are two contrasting methods that work on a nearby universe and very large scales. At the nearby universe, what we do is essentially a modification of what Hubble did, and we measure directly the recession velocity and the distance to the source. The distance measurement is not that direct, because it involves something called the cosmic distance ladder. There are nearby objects that you calibrate, and then some of these objects happen to be standard candle whose which are sources of known luminosity, and you can use these standard candles up to slightly higher distances, and then find other standard candles at higher distances, which can be used at even higher distances. And these three steps, there are multiple steps, and we would call each of these steps a rung in the cosmic distance ladder. In the recent state-of-the-art measurement that comes from the Shoes collaboration, Rice et al., we have these three rungs in the distance ladder that that is shown in the bottom right of the screen. Again, you calibrate things at lower distances, go up to slightly higher distances to find standard candles at higher distances that you can use at even higher distances. One does not need to emphasize the fact that at every stage of this calibration, some error can creep in. So our measurement is sensitive to the way we are calibrating this cosmic distance ladder. On the left-hand side, we see the other method by which we can measure the Hubble parameter. The anisotropies in the cosmic microwave background, as measured by WMAP earlier and now, are very sensitive to the cosmological parameters, and in particular the Hubble parameter. So from the temperature map, for example, one can infer a value for the Hubble parameter along with the other cosmological parameters. And on the plot in the center, we see two bands. The band on the left, the greenish band on the left, is the estimate that comes from the Planck experiment at large cosmological scales, which probes large cosmological scales, while the band on the right comes from the Rice et al. Shoes collaboration at nearby redshifts. And these bands do not overlap. This means that there is discrepancy between the two state-of-the-art measurements of the Hubble parameter. Can I please go over to the next slide? The take-home messages from this is that H0, in spite of being a crucial parameter in cosmology, its measurement is not yet free of discrepancies. On the bottom left panel of my slide 4, we again see a number of other slightly earlier measurements, and many of them do not seem to fully overlap. So the essential message is H0 needs to be measured better, H0 needs to be measured independently. Can I please go over to my next slide? Slide 5. I mentioned these Cepheid variables and supernova of type 1a as standard candles. Here I'm going to talk about standard sirens, and I will say that these compact binary coalescences serve as standard sirens because with them one can directly measure the luminosity distance, just like one can do with some of the standard candles. Our gravitational wave detectors are sensitive to both amplitude and phase evolution of the chirp signal. In the chirp signal that we see in the figure in the bottom, we see many cycles, and one can study from the phase evolution over the many cycles, one can get a rather accurate estimate of the masses. Independently, the amplitude depends on the masses, distance, and inclination. So one can plug in the masses estimated from the phase evolution back into the amplitude to independently obtain the distance and inclination. So this gravitational wave observation directly tells us the distance without having us to rely on any cosmic distance ladder. And this is great. This is an idea from Bernard Schutz in 1986, and the word standard siren was coined by Dan Holtz and Scott Hughes back in 2005. Can I go over to my next slide, please? Which is slide 6. So, although distance can be very directly estimated by these by these gravitational waves from compact binaries or coalescences of compact binaries, the measurement of recession velocity or redshift itself is not very easy with gravitational wave data alone. This is because the total mass is largely degenerate with the cosmological redshift. However, one can take input from electromagnetic observations, like we had an associated electromagnetic counterpart for this event. For other events, one might be able to use a galaxy catalog, get a set of redshifts from a galaxy catalog, and use that as an input. So, again, the essential messages: the gravitational wave observation, one can directly measure the luminosity distance. However, the redshift or the recession velocity is slightly difficult to measure. However, it becomes very easy if one can, if one has an optical counterpart, or one can identify the host galaxy. Now we are ready to go over to GW 170817 cosmology results. So can I please move to slide 7, which actually carries a lot of information and is a summary of almost the entire analysis and an illustration of the result in a simple form. We've already heard in the previous talks that this GW 170817 had an optical counterpart, SSS 17A, and the host galaxy was very quickly identified to NGC 4993. So one can say that the probability of one can calculate the probability of false association of this optical counterpart to this host galaxy, and the probability of false association is less than 0.004%. So we are very, very confident that 4993 is actually the host galaxy. Now, one can use the redshift, or equivalently the recession velocity of 4993 from this galaxy catalog, which are from the favorite galaxy catalog. However, some complications creep in, and that is because our universe is not smooth at small scales. Our universe is, in our universe there is matter, and matter is clumpy. So the galaxies get attracted towards local matter overdensities, and the recession velocity that we actually see is not just the Hubble flow velocity, but there are some peculiar velocities on top of the Hubble flow velocity. In terms of redshift, the redshift of an observed galaxy is not exactly the cosmological redshift, but there are some corrections to, but there are some additional effects that come in from peculiar motions of the galaxies. For this NGC 4993 itself, one can read off the recession velocity in the CMB frame as some 3,227 kilometers per second.
Archisman, there is a lot of noise from your side. Perhaps you can keep the mic a bit away from your. Or is it moving?
It slightly better? Is it slightly better now, Bala?
Yes, Archisman.
Okay, thank you. So for this host galaxy, the recession velocity can be read off from a catalog as this number 3,327. However, one needs to correct for the peculiar velocity. So one looks at the group to which this galaxy belongs, and one tries to estimate the peculiar velocity of the group. We have an estimate of about 300 kilometers per second, which is about 10% of the total velocity. And we can correct for it, as during the process of the correction, we see that the uncertainties go up quite a bit. However, the uncertainties are still smaller than the uncertainties that come from our distance estimates. Our distance estimates we see on the right as is 43 plus or minus 5 maybe is a lot more imprecise than the peculiar velocity estimate, even than the Hubble velocity estimate, even after the peculiar velocity corrections. Putting these two in together, one gets a point on the distance Hubble velocity plot, and in this plot we make sure we have the units right. And one can get a straight line through this point and 0, which gives us a very crude estimate of our final result, the Hubble parameter. Of course, the final results differ slightly from this crude estimate because our uncertainties in the distance are not very symmetric, and they result in a slightly asymmetric distribution in the Hubble parameter. So I move over to my next slide, slide 8. This is a final result which shows us the marginalized a posteriori probability density of the Hubble parameter given all the observations associated with GW 170817 and following a Bayesian parameter estimation. We again see the two bands corresponding to the Planck and the supernova experiments, which do not overlap. Our results are this blue curve, and if we had similar bands, then our bands would be these bands that are sort of bordered by the dashed and the dotted lines. So we do not have a very precise estimate yet. And that is why our estimate is quite consistent with both the inconsistent existing estimates. However, and I'd like to stress this, our estimate is totally independent of the cosmic distance ladder. So it's an independent estimate that is consistent with other existing estimates. And in principle, by combining estimates from future events, we can get more precise estimates, and we might be able to favor one value of the Hubble constant over another. I would like to move over to the next slide, which is slide 9. This is something that Arun talked about just some time back. There is a very strong degeneracy between distance and inclination. The gravitational wave amplitude from a binary that is far away but face on is can be same as the amplitude of a binary closer by, but viewed not quite face on, but closer to edge on. This results in a strong correlation between distance and inclination. As a result, the posterior probability densities that we obtain in the first place, there are posterior probability density on the Hubble parameter as well as inclination or cosine inclination, which we are directly sensitive to. And this joint constraint is shown on the figure on the left. The figure on the previous page, our main result is this joint posterior squashed in the vertical dimension, that is marginalized over the inclination to give only the H0 result. However, one can take the same joint posterior and marginalize over the Hubble parameter, or choose a particular value of the Hubble parameter. One can choose to do one of them and project it over the horizontal direction. Then what one obtains is the figure on the right. One can get constraints on the inclination angle, either marginalizing over the Hubble parameter or fixing the value of the Hubble parameter to some prior ranges. And here we see that if we have a slightly large values of Hubble parameter as suggested by the supernova experiments, then we start ruling out the inclination angle to better than 90% or so. Sorry, we start ruling out face-off configuration. That is, we rule out off-axis. We rule out on-axis viewing to better than 90% confidence. Can I go over to my next slide, which is slide 10, and my concluding slide for the EW 170817 analysis. So here we have the first standard siren measurement of the Hubble constant, where the gravitational wave observation gives us the distance estimate, and the electromagnetic observation gives us the recession velocity or the redshift. The result we obtain is completely independent of the cosmic distance ladder, so we are not at all sensitive to all the systematics that go into the cosmic distance ladder. We are consistent with both the supernova and the Planck estimates, but our consistency is largely because we do not have a very precise estimate yet. But the era of multimessenger cosmology has just begun. We expect ourselves to get refined estimates with more observations of various kinds. I'd like to move over to my last slide, which is slide 11. As I mentioned, following this process, one can combine information from multiple observations and get more and more refined estimates. And it was shown, for example, by Nisank and et al. That with about 10 independent observations like this, one can constrain the Hubble parameter to a few percent. There is the possibility that one sees an optical counterpart. However, one is not able to exactly measure the redshift of the counterpart, but is able to able to come up with a few potential host galaxies. And with this narrow beam around the optical counterpart with the potential host galaxies, one can combine information from a few events to get a good estimate. And there is also the case that one does not see an optical counterpart at all. Even when one does not see a transient optical counterpart, one can do an analysis with using cross correlation with a galaxy catalog, and it was shown by Del Pozzo in 2012 that with a few tens of observations, without any transient optical counterpart and using cross correlation with the galaxy catalog, one can still obtain a value of the Hubble parameter to about a 5% accuracy. The good thing about this is this method is also applicable for black holes, and we are seeing many more black holes than neutron stars in these LIGO observations. Some of us, including Walter himself, Ajit, and me, have been trying to extend this analysis to try to see if we can measure other cosmological parameters like the dark matter density, dark energy density of the universe. That is, that work is still in progress. With this, I'd like to thank all of you for listening to me and end my talk.
Thank you, Archisman. Any questions for Archisman?
Hello, Archisman. Is there any way to resolve this mass redshift degeneracy that you spoke about? Is there? Do you think maybe having several measurements will help in that, or knowing the spin or something will accurately help in that? The general question is there a possible way to measure the redshift independently in the potential future using purely gravitational waves?
So Rajesh, it would be good if ICTS mutes while I speak.
Muted.
Yeah. So Rajesh, very good question, and indeed, with only gravitational waves, one can break the degeneracy, and the degeneracy is strictly true only when there is gravity. If there is gravity alone, then the effect of mass is just to bring things down to lower redshifts. If there is something that has a cosmological redshift that cannot be disentangled from the effect of a higher mass. But as soon as there is matter, this degeneracy is broken. So for neutron stars, this degeneracy is strictly not true. However, the degeneracy is broken very, very weakly. It is broken. It would be broken by these tidal terms, which are functions of the object's intrinsic mass and not the redshifted mass. So if one is able to observe the tidal effects, one is directly able to observe, to some extent, the intrinsic mass of the source as opposed to the redshifted masses. So with these advanced ground-based detectors, it is possible to break the degeneracy enough to make any sensible measurement of the redshift independently. But with future 3G detectors like the Einstein telescope or the cosmic screw, there are already some papers written about it. One can actually look into these tidal effects and break this degeneracy between mass and redshift. I hope this answers your question.
Microphone activated.
Any other questions?
Archisman, this is Sukant. One question I have is, you mentioned that with binary black holes also you can determine the Hubble parameter purely with, more or less purely with gravitational observations. So we already have seen 4, and in O3 we expect, okay, let me give you a number. Let's say we see 20. Now, if you use this BNS H0, observation as a prior on your binary black hole observations, how well do you think your H0 determination can get, assuming that all your binary black holes in O3 are within 430 megaparsecs?
Yes. So again, can ICTS please
Microphone
mute?
muted.
Thanks. So, Sukant, again, a very good question. The plan would be to combine information from, I mean, there are two ways of talking about it. One can say that you use the previous information as a prior, or you can say that you just combine information as they come by. So the plan would, of course, be to combine information from all events that we see, and from Samaya's work and Walter's work, which are at low redshifts in the local universe, where you measure only the Hubble parameter and not the other cosmological parameters. One can see that one can expect of the order of 5% measurement on the Hubble parameter from about 10 BNS observations with counterparts, as well as from about 30 observations without counterpart. So one can get to the similar. One can get to a similar accuracy by a similar combination of events. So let's say we have 5 BNS events with a counterpart and 20 BBH events at these redshifts, where one can use the cross correlation approach reasonably well. I mean, this galaxy cross correlation approach is a bit tricky as you go farther away, because there are more potential host galaxies. The catalogs are incomplete, but at these low redshifts where they work, different combinations of the two can be put together to get a similar result.